Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic, math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.
Magnitude of the magnetic field. But now let's see what happens to the direction. So the right hand rule helps to determine the direction of the magnetic field due to the long wire. Grasp the wire in your right hand with your extended thumb pointing in the direction of the current. Your fingers will curl around in the direction of the magnetic field. So if you look at it here, see this is the current carrying wire and you see you curl your right hand fingers in such a way that they just grasp your current carrying wire. Then the thumb is pointing towards the current direction. Now the finger curling direction will be your magnetic field direction. So this law is given by right hand rule. So whenever you have a current carrying wire, if you want to find out what is the magnitude of or the direction of the magnetic field, then you can use the right hand rule. Okay. Now we have come to a special case called solenoid. So in the previous case we talked about a current carrying wire which had cylindrical symmetry because it was straight, and now we are going to talk about a solenoid. So what is a solenoid? A solenoid consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. So each turn can be regarded as a circular loop. So it is like this. There are so many coils like this. So we can take each turn as a simple coil. It's a circular loop. So we can assume that a solenoid is so many circular loops clubbed together. So this is a solenoid. And now if you see the current is coming here and going here. So if you see here, it is very clear. The blue dots represent the current coming in and this cross marks represents the current going in. So this is current coming out. This is current going in. Now the net magnetic field due to a solenoid is the vector sum of the fields due to all the turns. The turns are insulated from each other using enameled wires. The figures show the entire solenoid with magnetic fields. It is clear that the field between the turns cancel out. So what do they mean by that? If you see each of this current coils, there is a circular loop here which is the magnetic field. But if you see the neighboring coils, they cancel out because the magnetic field direction is opposite to each other because in everywhere it is in counterclockwise direction. So if you see this loop and this loop, if you see this loop and this loop, they cancel out. So the magnetic field between the coils cancel out. But what about the magnetic field here? So inside this, it almost looks like a magnetic field, uniform magnetic field flowing through this. But outside also it is very, very less and negligible. So we can neglect it. So as the solenoid is made larger, it appears like a long cylindrical metal sheet because all the circular coils are clubbed together. Now let's consider a rectangular Amperian loop ABCD. So this is a solenoid. Here this blue dots again represent the current coming out of the plane and this cross marks represent current going into the plane. B is the uniform magnetic field produced inside the solenoid, and point Q is outside the solenoid where the magnetic field is again negligible. So we are going to form an Amperian loop which is rectangular. So ABCD is the Amperian loop which is rectangular. Now we have to find out what is the magnetic field along each turn of this loop. So along this circumference of this loop we have to find out. So now this along the sections BC and AD, the field component is 0 because field only has this component. There is no field here or here. So we can assume that the field component is 0, and even Q also field component is 0. So let the field along AB be capital B. Now the relevant length of the Amperian loop is L equal to H. So now this is the loop length of the loop, because here and here everywhere the field is 0. So only the length of here H only survives. So that's why L equals to H here. If n be the number of turns per unit length, then the total number of turns is nh. If n is the number of turns, means number of coils per unit length, then how many coils will be there in h length? Then it will be n multiplied by h. The enclosed current is I equal to INH. I is nothing but the current that is flowing through in each loop. So what is the total current that is flowing here? I multiplied by n into h. Because NH is the number of turns in this area. I is the current inside every loop. So INH is the overall current in this area. Now from Ampere's circuital law, we know BL equals to mu 0 into IE. In this case, BL is nothing but the left hand side, that integral. In the right hand side, we have mu 0 IE. IE is the current enclosed. So what is the equation for IE? It is I multiplied by NH. So just cancel out H on both sides, then we get P equals to mu 0 Ni. See, this is the magnitude of this field. So what it tells you is, if you have a solenoid with n turns per unit length, then the solenoid's magnetic field is going to be mu 0 n into I. So if you want to produce a powerful magnetic field by using a solenoid, you can design it by using current I and by using this many turns per length. So this is the magnetic field value that the solenoid creates. And now we know the magnitude, so how do we find the direction? So the direction of the field is again given by the right hand rule. But now what do we do is, we curl the fingers of the right hand from the current direction. So the coils are like this, circular coils are like this. So in the same way we will curl the fingers. So whatever the direction of the current, we will curl the fingers, and the thumb direction will be the magnetic field direction. So thumb is pointing here, so that will be the magnetic field direction. What if the current is reversed? Then you have to curl your fingers from bottom to top. Then your thumb will be pointing towards the left. So if you change the direction of the current, the magnetic field direction also reverses. Okay, now we have come to the case of a toroid. So toroid is similar to a solenoid, but it is in a circular form. So you take a solenoid and you bend the circular loops in a big circular form, then this is called a toroid. So the toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. It can be viewed as a solenoid which has been bent into a circular shape to close on itself. A toroid which is carrying a current I is shown in the figure. The magnetic field in the open space inside, that is the point P, and exterior to the toroid point Q is 0. The field B inside the toroid is constant in magnitude for the ideal toroid. So the field inside the loop is also 0, the field outside is also 0, and the field inside this toroid is not 0, but it is uniform. So we are going to calculate that field. So before calculating that, we need to assume some Ampere loops, right? So in this case, we are taking 3 loops. So there are 3 Amperian loops, 1, 2 and 3 are shown by the dashed lines. The magnetic field should be tangential to each of them and constant in magnitude for a given loop. So let's look at the picture here. There is a loop here called 1 with radius R1. There is a loop here inside the toroid which is called 2 with radius R2, and there is a point S on it. And then there is a loop 3 which is outside the toroid with the point Q on it with radius R3. Now the circular areas bounded by loop 2 and loop 3 both cut the toroid. That means loop 2 is just going in the middle. So if you make a circular area out of this loop, open circular area, then it's going to cut the loop once. But if you take the 3, then it's going to cut the loop twice. Because it is outside, so it sees both the currents. Now let the magnetic field along loop 1 be B1 in magnitude. Then in Ampere's circuital law, we have L equal to 2 pi R1. The loop encloses no current, so I equal to 0. So what do we see here? Let's just take the loop I1. I1 if you take, it does not enclose any current because it is inside and there is no current in it. So the loop does not enclose any current, so I equals to 0. When I equals to 0, then B1 is also equal to 0. So the magnetic field inside this point is 0. And let's now look at the loop 3. Loop 3 also includes 0 current because the current whatever is coming out of the plane through the blue dots, here they go into the plane. So the total current enclosed inside this loop is going to be 0. So then Q also B equals to 0 in Q also. So the magnetic field along loop 3 be B3. From Ampere's law, L equal to 2 pi R3. And now we already talked about this. Current coming out of the plane of the paper is cancelled exactly by the current going into it. So that E equals to 0 and B3 is also equal to 0. Now what is the only loop that is left? That is loop 2. And now if you look at loop 2, what is the current enclosed in loop 2? That is just IE. So if I is the current through flowing through the toroid, then N into I is the total current given. So in the right hand side you have in the left hand side you have B 2 pi R2. In the right hand side you have mu 0 Ni. So finally you get B equals to mu 0 Ni by 2 pi R. So this is nothing but the magnetic field inside the toroid. So it depends on the radius R. That means at what distance you are looking at, what distance from the center you are looking at the magnetic field, and it depends on the number of turns and it depends on the current. So here also toroid can be used to create magnetic field. So one way to do it is if you want to control the magnetic field, you can play with the current or number of turns. Then it will the B will also change according to that. Okay, now we found out what is the magnetic field produced by a toroid. Now let's compare this with the solenoid. So in a solenoid, then we have instead of a circular wound wires, we have a straight line of circular coils, right? So then let R be the average radius of the toroid and N be the number of turns per unit length. If this becomes a solenoid, then we will get N equal to the total number of turns is equal to 2 pi R, that is the perimeter of the toroid, multiplied by the number of turns per unit length. So this will be the total number of turns. So then B equals to mu 0 Ni. If you substitute this value in the previous equation, then you will get B equal to mu 0 Ni, which is nothing but the result of the solenoid. So both are basically the same, both give the same result, and only the way they are is different. For a solenoid, the circular wires are kept in a straight line like a metal sheet, but here they are wound up in a circular loop like this. So in an ideal toroid, the coils are meant to be circular, but in reality, the turns of the toroidal coil form a helix and there is always a small magnetic field external to the toroid. Okay, so we talked about solenoid and toroid, and we already discussed about what is the magnetic field produced by a current carrying wire. Now that we are going to discuss what happens when there are two current carrying wires kept near to each other. See, a current carrying wire produces a magnetic field. At the same time, the current carrying wire experiences the force due to a magnetic field. So these both things are going to happen here. So a current carrying wire gives rise to a magnetic field which obeys Biot-Savarts law. An external magnetic field will exert a force on a current carrying conductor. This follows from the Lorentz formula. So, two current carrying conductors placed near each other will exert magnetic forces on each other. So, that's what we are going to calculate. What will be the magnitude of this force? Two long parallel conductors A and B are separated by a distance d and carrying currents IA and IB. The conductor A produces the same magnetic field BA at all points along the conductor B. The right-hand rule tells us that the direction of this field is downwards. Its magnitude is given by Ampere's circuital law, which is BA equals to mu 0 I by 2 pi d. Here we already saw this formula, B equal to mu 0 I by 2 pi r. Instead of r we have d. D is nothing but the distance between these. So this A is the magnetic field produced by the current carrying wire A. That's why it has the current source here as IA. So because of this current only, this magnetic field is produced, and this is at a distance t from this. So this is the magnetic field that is going to be experienced by this current carrying wire. So it's going to get a force because of this wire, because of this magnetic field. So we will see what is that force. So this is the magnetic field. So now the conductor B carrying a current IB will experience a sideways force due to the field BA. The direction of this force is towards the conductor A, and this is given by Lorentz force. And we label this force as FBA, the force on a segment L of B due to A. So the force on B due to A is given by FBA, and it is given by IBL into BA. So this comes from Lorentz force, if you remember, Q V cross B. So that becomes IL and BA. We talked about this in the last chapter. And now instead of BA, let's substitute this equation here. So then it becomes mu 0 IA IB divided by 2 pi D into L. So if you look at this equation, this gives you what is the force experienced by the current carrying element B because of the magnetic field produced by A. So it has the product of both the currents. So it is in some way it is similar to Coulomb's law, where Q1 Q2 by 4 pi r squared, 4 pi epsilon 0 and r squared. So the force is dependent on the product of both the currents and the distance between them and their length also. And now okay, if you reverse this calculation, if you do the same thing for what will be the force on A because of the current that is flowing in B at a distance t, that will be just negative of this value. So it obeys Newton's third law, where the forces are equal and opposite. So FBA is equal to minus FAB, right? So now this tells us that parallel currents attract and anti-parallel currents repel, because FBA is this way and FAB will be this way. So both the conductors move towards each other. If you look at the current direction, it is in the same direction. So when the current is in the same direction, the current carrying wires attract each other. So this is just opposite to electrostatic case, where the like charges repel each other and unlike charges attract each other. And now let's define a quantity called small fBA, which is nothing but the force per unit area, unit length. So in the previous equation, we had an L here. Let's take this L to the left hand side. Then we will get small fBA, which is nothing but force per unit length, which is equal to mu 0 IAIB by 2 pi d. Why do we do this? Because we have just calculated for a piece of wire here. We want to make this a common formula where we can use it for any kind of length. So then we will define force per unit length like this. And from this expression, actually we can calculate what is ampere. So the ampere is the value of the steady current, which when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to this much newtons per meter of the length. So we are using this formula to find out what is ampere. So if the distance, let's make the distance as 1 unit, and we know the value of mu 0, let's substitute it. Then if IA and IB also 1, then the value of FBA should be 2 multiplied by 10 power minus 7 Newton per meter. So this much current, this much force will be produced if both are having 1 ampere current. So by using this, we can define what is the value of 1 ampere. Okay, so in the previous case, we talked about two current carrying wires which are separate. But now what if we have a loop? So in this case, we are going to talk about a rectangular current loop which is kept in a uniform magnetic field. This is a very important concept which is used in both electrical generators and motors. So in motors, basically the electrical energy is converted into mechanical energy. In generators, the mechanical energy is converted into electrical energy. In both the things, this concept is used. So it's very important. So first we are going to consider a case where the loop is just horizontal along with the magnetic field. So we can say that the area of the loop is pointing upward, so it's perpendicular. So you see there is a bar magnet, or there is a magnetic field N and S, and there is a magnetic field flowing between these, and so this is the direction of the magnetic field, and we have a rectangular loop called ABCD, there is a current I flowing through the loop. So if you see, the current here is flowing from left A to B, here it is going from C to D. So the direction is opposite here. And let's see what is the force exerted on this loop by this magnetic field. The field exerts no force on the two arms AD and BC of the loop. Why? Because whatever force is exerted here will be equal and opposite to the force exerted on this. Like this, if you look at this, F1 is the force on this AB and it's pointing downward. Then F2 is the force on this CD which is pointing upward. Both are equal and opposite. So let's calculate these forces. The magnitude of the force F1 is equal to IB and B. And now similarly it exerts a force F2 on the arm C2 and F2 is directed out of the plane of the paper. So F2 equals to IBB which is equal to F1. So now you see two forces are acting. In one force in this end which is acting upward, in this end it is acting downward, and they are at a distance. So when two forces are opposite and equal to each other but they are acting at a distance, then we get a torque, right? So when there is a torque, then what happens? The loop rotates. Okay, so that's what happens here. So the net force on the loop is 0, but there is a net torque acting on the loop due to the pair of the forces F1 and F2. So how do we calculate this torque? So the torque on the loop tends to rotate it anti-clockwise in this case, and let's calculate the magnitude of the torque. Tau equal to F1 A by 2 plus F2 A by 2. So the force multiplied by the distance. So if you see here, the distance is A by 2 from the center point, and F1 is the force here, F2 is the force here. So they both are equal and the value is IBB. So let's substitute it here. So if you just take AB as common, then we get IAB into B. AB is nothing but the area of this loop. If you see, this B is the slide length, A is this length. So AB is nothing but the area of the loop. So we get IA into B. So the torque on a current carrying wire when it is horizontal is given by the product of the current, the area of the loop, and the magnetic field. Okay. Now what if this loop is kept at an angle theta like this? So the magnetic field and the loop, the area of the loop makes an angle theta with the magnetic field. Now the plane of the loop is not along the magnetic field, but it makes an angle theta with it. The forces on the arms BC and DA are equal, opposite, and act along the axis of the coil, which connects the centers of masses of BC and DA. Being collinear along the axis, they cancel each other, resulting in no net force or torque. The forces on arms AB and CD are F1 and F2. Again, now we have the forces on AB and CD. Again, it is F1 and F2, which is equal to IBB. These forces are equal in magnitude but not collinear. So this leads to a couple. Again, this torque, there is a torque, but this torque is less than the earlier case when the plane of the loop was along the magnetic field. This is because the perpendicular distance between the forces of the couple has decreased. See, in the previous case, the perpendicular distance was A, or A by 2 this side, A by 2 this side from the center. But now if you see, it is A by 2 sine theta because it makes an angle theta with the magnetic field. So that's why even now there is a torque, but this torque is not as strong as in the previous case. So now let's find out what is the magnitude of the torque. So now we have F1 A by 2 sine theta because this is the perpendicular distance, and plus F2 A by 2 sine theta. F1 is IAB and F1 is IBB. So you substitute that and then you get IABB into sine theta. AB is nothing but the area of the loop. So we get IAB sine theta. So what does this tell you is, if the loop is making an angle, the torque depends on the angle. So how much the rotation will be is decided by the angle theta. So let's assume that when the angle theta becomes 0, the perpendicular distance between the forces of the couple also approaches 0. So sine 0 is 0, right? So this makes the force collinear and the net force and the net torque will be 0. So the torques can be expressed as a vector product of the magnetic moment of the coil and the magnetic field. So if you take this IA as the magnetic moment and B as the magnetic field, then sine theta, this is nothing but the vector field, vector product. Okay, so let's assume that the magnetic moment of a current loop is defined as M equals to I into A. So then the direction of the area vector A is given by the right hand thumb rule and is directed into the plane of the paper. Now the angle between M and B is theta. So in the previous equation can be expressed as tau equal to M cross B, because here you see tau equal to IAB sin theta. Now IA is nothing but M, B sin theta. We can take this whole thing as M multiplied by B, and here it is nothing but a cross product or a vector product. Now this is analogous to the electrostatic case where the electric dipole of dipole moment PE in an electric field E is tau equal to PE multiplied by E. So the torque produced on an electric dipole is now similar to the torque produced by on an current carrying loop by the magnetic field. So can we say that the current carrying loop kind of acts like a magnetic dipole? Okay, so that's what we are going to see now. So circular current loop as a magnetic dipole. So the magnetic field on the axis of a circular loop of a radius r carrying a current I is. So this is the equation which we have derived. B equals to mu 0 I r squared by 2 x squared plus r squared the whole power 3 by 2. Now when x is much greater than r, we can neglect this term, because if x is much greater than r squared plus x squared will be almost equal to x squared. So we can neglect this r squared here. Then what about this direction? Its direction is along the axis and given by the right hand thumb rule. So whenever there is a magnetic field involved, we will always use the right hand thumb rule. Okay, so now after reducing this r square, now you get removing this r squared, now you get mu 0 I r squared by 2x cube. Now we know that A equal to pi r squared for a circular loop. And then if you substitute this pi r squared in this equation, then you get B equal to mu 0 IA, because instead of r squared you can substitute A by pi. Then you will get mu 0 IA by 2 pi x cube. Now we know that M equal to I multiplied by A. What is M here? Magnetic moment, which is equal to current multiplied by the area of the loop, right? So now let's substitute, instead of this IA, let's substitute M here. Then we finally get B equal to mu 0 M divided by 2 pi x cube. Now if you add it to both sides, in the numerator and the denominator, then you get mu 0 by 4 pi multiplied by 2m by x cube. Now this expression is very similar to the expression obtained earlier for the electric field of a dipole. So how is that similar? Let's see. If you substitute for mu 0 1 by epsilon 0, and if you substitute for m as P, that is electric dipole moment, and B is the magnetic field, instead of magnetic field if you substitute electric field, then you get this equation. E equals to 2p divided by 4 pi epsilon 0 into x cube. So these two equations are very similar, just that you have to replace the constant like this. So this is for a circular current loop and how it acts as a magnetic dipole. Now we know that any current is going to produce a magnetic field, and we know that a circular current loop acts as a magnetic dipole. So we are going to just look at an atom with one electron revolving around the nucleus like this. If this electron is continuously going in circle, can we consider this as a circular loop and calculate what is the magnetic moment associated with it? So that's what we are going to do. So according to the Bohr model of atom, the electron revolves around a positively charged nucleus. The force is electrostatic in nature. So why do we say electrostatic? Because it's a positive charge, this is a negative charge, and there is a force between them, that is electrostatic Coulomb force. Now the electron of charge minus E performs a uniform circular motion around a stationary heavy nucleus of charge minus ZE. This gives rise to a current I, where I equal to E by T. Why is it E by T? Because I equal to Q by T. Q here is E and T is the time of revolution. That means time period of revolution. How much time the electron takes for making one revolution. So T is the time period of revolution. If R is the radius, orbital radius of the electron, radius of this particular orbit, then V is the orbital speed. Then how do we find the time taken for a period of revolution? The distance traveled divided by the speed will give us the time. So the distance traveled in one revolution is 2 pi r, the circumference of the loop, and V is the speed of the electron. So we get T equal to 2 pi r by V. Then if you substitute this quantity here in this equation, then you get this equation I equal to EV by 2 pi r. So now the magnetic moment associated with this circulating current, we know magnetic moment is equal to M equal to IA, right? So we have the equation for I, and we know what is A. A is nothing but pi r squared for a circular loop. So mu L, that is the magnetic moment, equal to IA, which is nothing but I pi r squared. And let's substitute the value of I here. So we get I, instead of I, if you substitute EV by 2 pi r multiplied by r squared, then you get EVR by 2. So this is nothing but the magnetic moment associated with the circulating current. That means if one electron is revolving around the atom, it produces a magnetic moment. It acts as a magnetic dipole moment, and it gives rise to this much values. So that's what we calculated. Now, what will be the direction of this magnetic moment? It will be into the plane of the paper. Again, we will use the right hand rule. And now, so yeah, by using the right hand rule, you curl your fingers along the direction of the current. Now, you should remember that the direction of current is always opposite to the direction in which the electron is moving. So if you curl your fingers from here to here, then your thumb will be pointing into the plane. So then that's why we have magnetic moment is going into the plane. Now the value is EVR by 2. And now let's take the value of mass of electron and let's multiply this and divide this by the value of mass of the electron. Then we have E by 2 ME into MVR. See, MV is the momentum, linear momentum, R is the radius. So if you multiply radius of, R is the distance. If you multiply this with the linear momentum, you will get the angular momentum. So L is nothing but the angular momentum, orbital angular momentum of the electron. So the negative sign indicates that the angular momentum of the electron is opposite in direction to the magnetic moment, because magnetic moment is going into the plane. So it is always opposite to L. But if you have a positive charge, then there will not be a negative sign here. So mu L equal to E by 2 ME into L. This is an important equation because this angular momentum is happening because of electron revolving around the atom. How that gives rise to this magnetic moment, that is what this equation tells us, how they are related. Okay. Now, yeah, we already talked about this. If you have a positive charge, then the magnetic moment value will be along the angular momentum value. Now, let's take the ratio between these two. So, we are just going to bring this L to the left hand side. What do we get? E by 2 ME. So, this quantity is called gyromagnetic ratio, and it has a value of 8.8 multiplied by 10 power 10 coulomb per kilogram for an electron's mass. So now let's define angular momentum from the quantum physics point of view. So in the classical physics, actually any quantity can take any values, there is no limitation. But in quantum physics, the quantities have to take discrete values. So in this case, if you see L equal to NH by 2 pi, N is a natural number, H is a Planck's constant. So N has to be an integer. So if you look at this L equal to NH by 2 pi, L can take only values where N ranges from 1, 2, 3, 4, 5, etc. So N cannot take values like 1.5, 1.6, 1.7. So the L value also have to be in discrete values. For example, for N equal to 1, L takes H by 2 pi. N equal to 2, L takes 2H by 2 pi. N equal to 3, L takes 3H by 2 pi. So these are the only allowed values an angular momentum can take for an electron. So what is the basic value for this? Let's substitute N equal to 1 and substitute Planck's constant and 2 pi and find out what is the value. So it is given as 9.27 into 10 power minus 24 ampere meter squared. So this is the unit of magnetic moment. Thank you.
Why waste time in commute and spend a lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com